In this video, we calculate the surface area of a tetrahedron, and in particular, this area here that I'm going to draw. And we are going to do it in two ways. First, we are going to calculate it by means of a surface integral, and then we are going to calculate it with the divergence theorem. Now, the surface area that we want to calculate is something like this. I'm going to sketch it. We have four faces, since it's a tetrahedron, and the faces are this one on the xy plane that I'm going to call surface number 2, because I'm going to call this one as surface number 1. Then I have 3. Surface number 3 is the one on the yz plane, and number 1 is on the xz plane. And then I have number 4, which is the slanted surface, this one here, which is described by the following plane: x plus y plus z equal to a. And therefore it means that this side that I'm going to highlight in red has a length equal to a, this one here has a length equal to a, and this one here has a length equal to a. Now we can define the function f of x, y, z equal to x plus y plus z minus a, which is of course equal to 0 because of this equation here. But this will help us find the normal to the surface, so we will use this during our second solution when we use the divergence theorem. The first solution that we will find is by means of surface integral, so we will not need the normal there, as I will show you, but let's find the normal because it is very easy. We just have to take the gradient of this function, so it's 1, 1, 1, and then we want to normalize it, therefore we divide by the square root of 3. Now, the surface is given by the sum of the surface S1 plus the surface S2 given by this surface here. Then we have the surface S3, this one, and then we have the surface S4. Now, the surface S1 is equal to the surface S2, which is equal to the surface S3, and therefore this sum here is going to give me 3 times the area of this triangle, for example. So that area is simply a squared over 2, just like this. And now we want to find the surface S4, and we can compute it with the surface integral. In particular, it's integral over ds, where we are integrating over S4 here, this area. And this can be calculated using Cartesian coordinates in this manner. You can check my course on multivariable calculus, but you can also find this everywhere online if you just check. So I also gave a proof in my course. You can find one, it's simple one. I'm not going to do it here. You have integral of the square root of 1 plus the derivative of the function f, which is this one, with respect to x, plus the derivative of f with respect to y, and you have to square df over dx, and you also have to square df over dy, like this. Then you have dx dy, and this is a simple calculation because the derivative of f with respect to x is just 1. This is also 1, so you have the square root of 3 times integral dx dy, and therefore we have to integrate over the projection of the surface S4 on the xy plane, but that's exactly this triangle here. So we already know the answer. We will get square root of 3 times a squared over 2. But if we want to calculate it as a double integral, this is square root of 3, and then we integrate from 0 to a, because the variable x can go from 0 to a, whereas the variable y can go from 0 to a minus x, because y goes from the value 0 here to this line, which has the equation y equal to a minus x. And you can obtain this equation simply from the equation of the plane here, which describes this slanted surface, and you simply set z equal to 0 because we are on the xy plane. So what you get is simply y equal to a minus x. So you integrate from 0 to a minus x dy dx. And the result of this integral is very trivial. You get square root of 3 times a squared over 2. And therefore, it means that s is equal to 3 plus square root of 3 over 2 a squared. Now, we want to get this result also by means of the divergence theorem, which is not so straightforward if you think about it. And this is due to the fact that the normal, written like this, is not continuous actually, because we have the normal, which is this normal here, and this is normal to the S4 surface, so to the slanted surface. But for example, if you want the normal to the S2 surface, so let's call it N2, well, this goes down like this. So this is equal to 0, 0, minus 1. And we have done a similar exercise before this one, where I calculated the surface of a cube by using the divergence theorem. So the intuition is the same. And I have done that also for a sphere, but for the sphere it was much easier. We had a continuous normal after all. But in this case, we are going to assume that the normal is defined only on the faces, whereas inside the volume of this tetrahedron we have that the normal is 0. So for example, let's consider the z component of the normal. So the z component of the normal, be it n or n2. So we think of n as a function, and we will see that when we take the derivative we will get Dirac deltas as in a previous exercise. So the normal is a function like this, nz. Nz, as you can see, if z is less than or equal to 0, we can define this function as z to be equal to minus 1. So here we have minus 1. And this is z equal to 0 here. And then, when this function here is equal to 0, we have that the normal is, the z component of the normal is 1 over square root of 3. Right? So this is the difference with respect to the cube, because in this case, this point here is defined like this. It is such that x plus y plus z minus a is equal to 0, which means that z is equal to a minus x minus y. So it also depends on x and y, of course, because if you are at the point 0, 0, 0 and you go up, you're going to reach the point a here. So the normal at the point a will be 1 over square root of 3, the z component of the normal. Whereas, for example, if you're at this point will be the point 0, a, 0, right? So this equation here is still satisfied because x is equal to 0 and y is equal to a, and you're going to get z equal to 0 in that case. So the height, which means z, will be different if you are here, here, also here. It depends on where you are. I hope you understand that. But after this point, so maybe I could lower this point a little bit, because the height of this point here is going to be 1 over square root of 3. And then after this point, we will define it to be 1. So we have two discontinuities. One discontinuity is at this point, and the other discontinuity is at this point. So the normal is defined as 0 inside this region. And if you take the derivative of nz with respect to z, you're going to get two Dirac deltas. One Dirac delta here will be 1 over square root of 3 times the Dirac delta, because the height of this step is 1 over square root of 3. So the Dirac delta is multiplied by the height of the step, which is 1 over square root of 3. And then this function will be a function of x plus y plus z minus a, which means that when this argument is 0, you're going to get an infinite value there. And this is z, and then you are going to get another positive Dirac delta. In this case, the step was the height of the step was 1, because we go from -1 to 0. This Dirac delta is still positive, and it is delta of z, because it is centered at z equal to 0, right? And therefore, if you want to find the total surface of our tetrahedron, we have to integrate over the volume, and then we have the divergence of the normal, which we think of as a function, but in this case it is not really a function. I mean, the divergence of this is not really a function, because we get Dirac deltas. But Dirac deltas are very powerful because they will allow us to find the result. So here we integrate, and then I'm going to put, so here I have dnx over dx plus dny over dy plus dnz over dz. And if you think about it, so I have dx, dy, dz, and if you think about it, this problem is actually symmetric. So we can integrate only, for example, dnz over dz, and then multiply the result by 3, because you're going to get something similar for the derivative of, for example, nx with respect to x, and you're going to get something similar for the derivative of ny with respect to y. So you're going to get the same triple integral. So you can do this derivation here and simply add 3 triple integrals, or you can simply write this as 3 times the integral over the volume of dnz with respect to z, and then here you integrate first over z dy dx, and then here we can also rewrite the limits of integration. We have integral from 0 to a, this integral will be over x, then we integrate from 0 to a minus x, this is the integral over y, and then we have the integral from 0 to a minus x minus y, this is the integral over z. But we will replace this function here, which is not really a function because it contains delta, with these two deltas, and we have to sum them. So we have delta of z plus 1 over square root of 3 delta of x plus y plus z minus a, and then we integrate over dz, dy, dx. So when we integrate over the two Dirac deltas, we are going to get 1. So we have integral 0 to a, integral 0 to a minus x. When we integrate this first delta, we get 1, then we get plus. This is going to yield 1, so we get 1 over square root of 3 times 1, like this, dy dx, and this is 3 plus 3 over square root of 3, and then we get the area of the triangle if you want, because we have to integrate from 0 to a, integral from 0 to a minus x dy dx, which is the area of the triangle whose surface we called S2, right, this one here. So we're going to get a squared over 2. You simply have to calculate this double integral, but you're going to get a squared over 2. And here you can rewrite this as 3 plus square root of 3, so I'm going to rewrite 3 over square root of 3 as square root of 3, then divide by 2 and multiply by a squared. And lo and behold, we got exactly the same result that we got here. So also the divergence theorem works in this case.